Hello, good evening. So, yeah, I guess we can start with today's lecture. Yeah, so this lecture would be about the summary of week 6, all the lectures of week 6. And yeah, I'll also be solving questions from last year's question paper, not just uh, with R, but also like the mathematical way. And I'll also show you a demo with R, like how you practice and visualize stuff in it. So yeah, this week was all about distributions. So we saw about 4 distributions, like the 3 major distributions. So yeah, let's get started. So the first one is a Bernoulli trial. So Bernoulli trial or distribution is useful when there are only 2 possible outcomes, like uh, a success or a failure, yes or no, like a male or a female, like where there could be just 2 possible outcomes. So, and our interest lies in only one of these outcomes. And so these outcomes are usually denoted by the values 0 and 1. And suppose, you classify this as a success or a failure. So this is what you call a Bernoulli distribution. And we all know that the probability of a success is P, and the probability of failure is 1 minus P. So the PMF is defined in this way, where P if X is equal to 1 and 1 minus P if X is 0. And the CDF for this case would be defined as like 0 if you get nothing, if there's a failure, and 1 if there's a success, and anything. So CDF is like a cumulative function. You just add up things. So anything that's in between 0 and 1 would be 1 minus P. So, and also from this, you can calculate the expectation and the variance. So expectation, like we know, it's the summation of g of x into like f of x, the probability function. So g of x is usually the value. Here in this case, it's just 0 or 1. So 0 or 1 multiplied by like the upper limit minus the lower limit at a specific point. So in this case, like at 0, you do 1 minus p minus 0. And then for 1, you do 1 minus 1 minus p. So 1 minus 1 minus p gives you 1 minus 1 plus p. So solving for this, you just get p. So this is the expectation, and this would be your mean. And similarly, expectation of x square would be you just square up these. And here E of x square is again p. And now we have already seen that variance can be calculated by E of x square minus E of x the whole square. Substituting like p minus p into p, like p square. So this gives, so p is common here. This gives you 1 minus p. So this is your variance. So you have the expectation and you have the variance of a random variable x. And also, like, yeah, so the most widely used examples are like a toss of a coin. Like you say it's a success if you get a head, and if it's a tail, it's a failure. And yeah, so the probability of these 2 outcomes are mutually exclusive and they are exhaustive. So this again means that one outcome doesn't depend on the previous outcome, and they're exhaustive. So you just have 2 outcomes, yeah, like head or a tail. You have no other outcomes in the sample space. So that's what you call exhaustive. So like, yeah, we have this Bernoulli trial. So when you conduct multiple such Bernoulli trials, so it follows a binomial distribution, so which is denoted by something like this. So n is your size, the number of trials that you perform, and p is the probability of a given outcome. So yeah, all these are independent trials or repetitions of a Bernoulli experiment with the probability of success is p and failure is 1 minus p, like we saw. So the goal of this binomial distribution is to see how many successes do you get. So like how many k successes do you get out of n number of trials. And you don't worry about the order. So you don't worry about like in which trial do you get the success. or what order of the trial, all you get these k successes. The order doesn't matter here. You just want to know how many successes in n number of trials. So yeah, like a course is tossed 10 times and you get 7 successes. Yeah, it could be like this. You could follow any pattern. So to model this, you do a binomial distribution. And yeah, to represent it mathematically, so yeah, this would be the formula. So K is your successes or whatever the outcome you're interested in, and N is the total number of trials. So you choose K out of N. So N choose K into probability of the success. So P number of successes. So P power K and the failures. So probability of the failure is 1 minus P, and number of failures would be N minus K. So even if you don't remember this formula, it's easy to like derive at this. So yeah, the PMF for X is equal to K would be this formula. So N choose K, P power K, 1 minus P power N minus K. And yeah, this is just a representation of this. Sorry. And it also follows a PMF denoted by this. So if K is any number ranging between like 0 to N, your the probability follows this function, and it is 0 if otherwise. So yeah, here's a simple diagrammatic representation of it. Here you can see that you're given with the values of P and N. So you have these values, and we could see that the probability of this green distribution and this purple distribution, the probabilities are the same. However, you can see that there's a different sample size. So for green, the sample size is 20, and like the number of trials is 20, n is 20, and here n is 40. So you can see a shift in the curve. So because there are more number of trials and the probability is 5, you get something, your mean is something around here. And same for this. So this is how your distribution just looks like for different n and p. Yeah, we already saw this. Oh, we didn't see this. So yeah, again, the mean of your distribution would be n into p, and your variance would be np into 1 minus p. And yeah, so Bernoulli random variable is b of 1 comma p distribute. So the next type of distribution is Poisson distribution. So this comes into play when the number of events, like your n is very large, but your interested outcomes is very few. So yeah, consider a situation in which the number of events is very large and the probability of success is very small. So the success is usually a countable number of events. So you could just easily count them. So in case of such a distribution, you use this Poisson distribution. So yeah, the typical examples that are given are like you have a book of thousands of pages and you just have a few number of misprints. So to model this, you use Poisson distribution, a finite number of outcomes for a large number of large number of events. And also the number of people in a living city to 100 years of age. So to like find this, you have to sample a large number of people. But the number of people living the number of people who are 100 years old would be just a very few. So this is again one example. And this is the formula, the PMF, probability mass function, for the Poisson distribution. So here you have something called lambda. So lambda is nothing but a product of n into p. So, and in case of Poisson distribution, the mean and your variance is equal. Your mean is equal to your variance, and both of these are given by lambda or n into p. So in like some of the the numerical questions that you get, you are either given, you're directly, in the statement, it is directly mentioned that the mean, which is lambda, the mean is 20 or something like that. Or if not this, you might have something like n number of 100 events, like 100 trials were conducted and the probability is given by this. So when in such a case, you can just arrive at lambda by multiplying 100 into 0.5. So yeah, you'll be given either of these estimates when you need to solve this kind of a problem. So yeah, the probability mass function for P of x is equal to x is given by lambda power x into lambda power x e power minus lambda divided by x factorial. So yeah, x is k. So it can also be written as power k e power minus lambda divided by k factorial. And also you could see how the curve shifts for different values of lambda. So if the mean is smaller, you can see that the peak is shifted towards your left. And for larger values of lambda, like this blue curve, you can see that your mean is shifted towards the right. You can see the peak here that is shifted towards the right. And also, it also makes sense that your variance is higher and the spread is also much higher in this curve. Whereas like your variance is smaller here, the spread is also like it's very small, the curve. So yeah, those are things that make sense when you think about it. And yeah, so here's just an example. Yeah, here's an example. So suppose a country experiences 4 earthquakes on average per year. So this is the meaning. Sorry, this is the mean. So 4 earthquakes on an average per year. So this is the average mean. And then the probability of suffering only from 2 earthquakes. So here k is equal to 2. 2 earthquakes is obtained using this distribution. So you just need to substitute uh, lambda power k e power minus lambda by k factorial, right? So lambda is 4, lambda power 4. Sorry, lambda is 4. Lambda power k into e power minus lambda divided by 2 factorial. So when you solve this, you'll get the probability for k earthquakes occurring. And you can also use to solve like such instances. So suppose the average number of accidents occurring weekly on a particular stretch of highways is 3. So average, it's given that the average. So we know average is the mean is lambda. So lambda is 3 here. So you need to find the probability that there is at least one incident in this week. So what does at least mean? At least one means 1, 2, 3, anything above 1. So the least, it has to be at least 1. So this can be given by P of x greater than equal to 1. So this can also be written as 1 minus P of x is equal to 0. And you just need to do 1 minus, you apply k is equal to 0 in your equation here. So yeah, we have lambda 3, lambda power k 0, exponent of minus lambda, which is 3, divided by 0 factorial, which is k. And you just substitute these, like this is 1, this 0 factorial is also 1. So you just have 1 minus exponential of minus 3. So solving this, you'll get the value for at least probability that there's at least one accident that week. And also, Poisson distribution also has an additive property. So when you add two distributions, like lambda 1 plus lambda 2, the distribution of the outcome, like the summation of these two, will also follow a Poisson distribution. So let's just look at an example here. Suppose the probability that an item is defective. So here it's given probability is 0.1. Assuming that the quality of successive items is independent, we know that all these trials are independent. The probability that a sample of 10 items, so n is equal to 10 here, probability of 10 items will contain at most one defect. A defective item can be obtained. So for this, you can use either binomial as well as Poisson distribution. So what do you mean when they say at most one defect? At most, maximum one defect. So you can have 0 defects or you can have one defect. So you need to calculate this, like x is less than or equal to 1. This is what you need to calculate. So this can also be written like a sum. You just need to calculate these two. So P of x is equal to 0 plus P of x is equal to 1. So if you apply a binomial distribution, you just substitute these values n and p in this equation here, like n choose k. So here k, these are the values of k. 0 and 1 are k. So n choose k, p of k into 1 minus p, n minus k. So this is the formula for binomial distribution. So in place of k, you just substitute 0 and you have these values. You substitute this, and you add these and you get the final answer. So even in case of Poisson distribution, you can substitute like k, and so n into p would be lambda. 0.1 into 10 is 1. So lambda is equal to 1. So you substitute these and add these and you'll get the answer. So we just saw that Poisson distribution has an additive probability. So lambda 1 plus lambda 2. So like lambda 3 would be summation of this. And even this one would follow Poisson distribution. And also it's a recurrence relationship. So when you calculate the Poisson distribution for k is equal to a specific value, you can also calculate p probability of k plus 1 or p of k plus 2 using this given formula. When you already know what p of k, like at the probability at k is this, you just need to multiply lambda by k plus 1 multiplied by whatever value you get here. Yeah, so you just need to multiply these to obtain like the recurring probabilities. So the final distribution is the geometric distribution. So here in binomial distribution, we saw that we were interested in the number of successes, like k number of successes out of n trials. And we did not worry about the order there. But here what happens is you don't have n trials. You just conduct trials and you stop the experiment whenever you get a success. Let's say you get a success at the 5th attempt. So that is your kth attempt. The attempt where you get a success is the kth attempt. And all the attempts before that is k minus, yeah, it's just like k minus 1. So this means that at the 5th attempt, you get a success. But until your k minus 1th attempt, which is the 4th attempt, it is a failure. So here you're interested in at what point do you get the success. So here k doesn't mean the number of successes. It means the value at which you get the success. So this is the major difference between binomial distribution and geometric distribution. And yeah, so this can be modeled using this formula here. So yeah, again, the same. The PMF is defined by P of x is equal to k, where like P, the probability of the success happens at kth trial, and the probability of failure is 1 minus P. And how many failures do you have? You have k minus 1 failures. So like 1, first, second, third, fourth, fifth attempt. This is a success. How many failures do you have? 1, 2, 3, 4 failures. 4 failures and 1 success. So yeah, this is the formula that you used for a geometric distribution. And the mean of a geometric distribution can be given by 1 by p minus 1. And the variance is given by 1 by p into 1 by p minus 1. So these are a bit hard to derive. There's a lot of integrations involved. So we're not getting into the details of that. So, but yeah, you can just remember these. And yeah, one more instance where you can use geometric distributions is when you don't have you have two things, like you have n white balls and m black balls, like you have n and m different things, and these balls are randomly selected one at a time until a black ball is obtained. So here the success is considered as the attempt when you get the m ball. So m is a black ball. So now let's say you need to find the probability that exactly n number of draws are needed And you also want to calculate at least k draws are needed, like p of x is equal to n and p of x is greater than equal to k. So you need to calculate these. So these can be calculated using these formulas here. So n was the failure, white ball, getting a white ball is considered a failure. And getting a black ball is m, black ball, this is a success. And this is a failure. So here you're calculating the probability that exactly n draws, that probably that you need exactly n draws to get a black ball. So this can be modeled with the formula. It's the same thing. So basically you have p into 1 minus p into k minus 1, right? So n is just k here. And the probability of getting a black ball would be m, a number of black balls divided by total number of balls, which is m plus n. This is p, right? And your failure is when you get a white ball. So a white ball divided by total number of balls again. And so here it will be n minus 1 or k minus 1, whatever is convenient for you. So this is how you get this. And when you just solve this whole thing, you will get this value. So whenever you see a question that looks like this, earn contains n white and black, and you want to calculate which draw do you get the success, you just apply this formula. And now there's one more thing. Probability of at least k draws. Just a second. Yeah, probability that at least k draws are needed. So which is p of x greater than equal to k. So this can be since the probability that at least k trials are necessary to obtain success is equal to the probability that first k minus 1 trials are failures. So k and k minus 1 are failures, we know that. So in this case, you apply this 1 minus p power k minus 1. So yeah, again, we have this p is equal to m by 1. And when you apply this, you get this thing that you should remember. So when you want to calculate p x greater than equal to k, you directly apply this. And yeah, one of the students in Friday's live lecture had raised a good question of why this is x greater than k. So we just saw that you get the success at the kth trial. And all these are, so this is the k minus 1 trial. And all these are failures, right? So basically this is p and this is 1 minus p power k minus 1. So this ideally should be x less than equal to k, right? But why in this equation there's p of x greater than equal to k for the same value? How did we get this? So yeah, let me just do a quick derivation of this so that it's easier to understand. So we know that the probability of mass function p of k is equal to x is 1 minus p into k minus 1. 1 minus p to the power k minus 1 into p, right? So this is having k minus 1 failures followed by 1 success at the kth trial. So and then we have the CDF, the cumulative distribution function is the probability that the random variable is less than or equal to a specific value. So for this, a geometric distribution can be given by x greater than equal to k. This basically can be expanded as p of x is equal to k because there's an equal to plus p of x is equal to k plus 1 plus p of x is equal to k plus 2 plus and so on. So this can just continue until the point where you get a success. So now we substitute the expression for p of x is equal to like k here. Like we just substitute this in this equation. So now what do you get? P of x greater than equal to k is equal to, what is p of x is equal to k? 1 minus p power k minus 1 into p. The same thing is written here. Plus, now what is this? P of x is equal to k plus 1 would be 1 minus p power k minus 1 plus 1 into p. So these get cancelled out. So you just have k left here in the power. And then we have p of x is equal to k plus 2. So in this case, it will be 1 minus p power k minus 1 plus 2 into p plus and so on. So when you solve this, you will have this thing will become k plus 1, right? So now what do you have? 1 minus p power k minus 1 into p. So in everything, you have this p as a common factor. Yeah, so in all of these, you have p as a common factor. So let's just, let me just take that out. So you have p as a common thing. No, actually you have all of this whole thing common. You have p and 1 minus p power k minus 1 is common in all of these. And this term becomes 1 because we take this whole term out of the bracket. Plus you have 1 minus p power k. You have already taken k minus 1 out of the bracket. So here you'll just have 1 minus p plus here you have 1 minus p power k plus 1. You've taken k minus 1 out. So you'll have 1 minus p power 2 here. So this goes on like this. So when you see a pattern like this, so 1 plus 1 minus p plus 1 minus p the whole square, your next term will probably be 1 minus p the whole cube and so on. So this is something called a geometric series, and it has a common ratio of 1 minus p at the first term. So, and yeah, this sum will go on until infinity, like whenever you get the success. So this thing can also be rewritten as this term can actually be rewritten as 1 by 1 minus 1 minus p is the common term here, right? So that common term it goes into this 1 by 1 minus whatever term is there. So on solving this, you get 1 minus 1 plus p. So 1 and 1 Hello. Yeah, I'm sorry. Like I have had a really bad internet connection. So can somebody just tell me where I got disconnected? Like, oh, maybe I'll just share my screen.
Probability of x greater than or equal to k.
Okay. So I was deriving that. And
Mm.
thank you. Let me share my screen again. So yeah, I hope until this was clear.
It is 1 minus p whole power k minus 1 into p, or
No, it's just this. So for k, x is greater than equal to k, it's just 1 minus p power k minus 1. Like it
only
is.
that. So, okay. Understood. Thank you.
Oh, okay. So before we solve these problems, I'll just go through R. I'll just reshare my screen. R is on the computer. Let me share the R screen. Let's- So yeah, in this R session, we'll look at how we can visualize these different distributions. So these functions are mostly like the format of this would be the same for all the three distributions that we saw, like for binomial distribution, for Poisson, and for geometric distribution. So yeah, let's first look at binomial and Bernoulli. It's basically the same thing. Like Bernoulli is just a trial. Multiple Bernoulli trials is a binomial distribution. So you have four things. Yeah, so you have D binom. So this is when you want to find the PMF, the probability mass function. So you have the D binom. Just a second. Mm. Yeah, so D binom is when you want to calculate the PMF, and you have something called P binom. You use this when you want to calculate the CDF, and there's Q binom that you use to find the quantile, like the value at which there's a specific you observe the 60th quantile or so. And then R binom um, to generate random numbers for that follow this particular distribution. So you use binom in case of binomial distribution. So there's D binom, P binom, Q binom, and R binom. So same goes with Poisson distribution. You'll have D poise, P poise, and R poise. And for geometric distribution, you'll have D geom, you'll have P geom, Q geom, and R geom. So it's basically the same format and it means the same thing. And now, so what are the variables you need to define here? So we saw that in all the cases we had some n value, we had a p and we had k. So your n basically is the size and k which is your X, the number of trials, and probability P is this value here. So let's just see, like for size n, given a probability 0, 3, like for 0, like 1 to 30K observations, what is your distribution? So these are all the values of your distribution. So when you plot a function, you have to define plot x comma y. So in your x-axis, you want all these values 0 or 1 to 30. In your y-axis, you want all these values. So you just write this whole thing in your y-axis. Or you can also like define this in a variable, and you can just write plot 1 to 30 comma y. So either of these, like whichever you feel comfortable with, you could use it that way. Let's see how this distribution looks. So yeah, you could see the distribution looks like this. So you can see that the mean, it follows something around 8 to 9. So this is your mean. And yeah, you could also like calculate the mean like this. Mean of D binom should give you 0.3. Okay, that's weird. Okay, yeah, let me just get back at this. Maybe I'm just doing something wrong. Okay, yeah, just to plot the distribution, so this is what you use. And let's see what happens when you just play with these parameters. So let's say we increase n to 100. Let's just plot that. So we have a distribution that looks like this. Basically, it just has more number of points, and you can see the peak here, and you can see all these values over here. So now let's say your n is 100, but you know that you get successes, enough number of successes, like 30% successes you get within your 100th trial, but still you continue your experiment for 500 trials. So in this case, what do you get? So you'll probably get a peak here and 0 until 500. Like after 100, all your values would be something like a flat line. So let's just check that. Yeah, like you could see, so your probability was 30, like 30%, like 0.3 probability for 100 trials. So you should get your successes something around 30. So you can see the peak around 30. And after that, it's all like 0. There's nothing here. So this is what happens when you increase your K beyond your N. And let's say we have N is equal to 500. And your probability is 0.3. So 30% of 500 would be something around 170. So your peak will be expected somewhere around 170. But here you just plot 1 to 100. So what will you see? You probably won't see the distribution reaching its peak or something like that. So yeah, you could see that it's increasing close to 100, but you haven't plotted anything beyond this. So you'll probably see the peak around 170 over here. And when it goes until 500, you'll see the whole distribution curve. So this is what happens when, yeah, you use different values of N and K. So you have to use the right values to get a good, like correct distribution. And yeah, here we're just trying to, it's the same. And now the next thing is P binom. So P binom is when you want to calculate the CDF. So we know that CDF, so in this case, we saw a peak like this, but CDF is a cumulative function. It's a non-decreasing monotonic function, which means it doesn't decrease. You don't see a decreasing curve. It just goes to the peak. It probably keeps going, and it might probably like flatten out. So yeah, it's you have the same things here, size, probability, but here the thing is for D binom, no, sorry. Yeah, for P binom, you use something called Q is equal to 1 to 30. So this basically means just 1 to K. And when you use Q binom, you use P is equal to, it's just how the notation is. That it doesn't mean anything. It's just, yeah, you just have to know that the first term that you give here is the number of, it's your trials. What were we doing? We were looking at Q binom. So we wanted to plot the CDF. So this is like a coin tossing experiment. You toss 3 coins. So for when you toss 3 coins, you'll have the sample space would be 8 outcomes, like head, 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 tail, tail, and such combinations. You'll have 8 outcomes. So your probability, if it's a fair coin, your probability basically should be 0.5. If it's like a biased coin, like maybe a coin with a bump on one of its sides, if it's a biased coin, your probability would be something else. So let's just maybe go with an unbiased coin, and let's look at what the CDF looks like. So, and yeah, your K, let's say you toss 3 coins and you're interested in getting heads. So getting a head is the success. So you could either have 0 heads, 1 head, 2 heads, or 3 heads. And your K cannot be more than 3 in this case. So you just write 1, 0 to 3. And yeah, the same things here. Like P binom, this is your distribution. P binom, Q is equal to 0, 3. So, sorry. So yeah, you could. Yeah, this cannot go beyond. So you could see that this curve, like it's increasing over here. CDF is like a non-decreasing function, so it will just keep going to its peak. And let's consider some other experiment here. Yeah, so here the size is 30. It's a much higher size. Here we just have 8 outcomes. So your curve looks like this. You don't see any pattern over here. I mean, like it's not like it's not like a visible pattern. Like unless you pay attention to the details, you can see that it's increasing. But as soon as you look at it, yeah, it doesn't look like anything. So let's just increase your n to 30, and we have something of a probability 0.3, and you again plot this. So yeah, here you can actually see how the CDF would look like. To look like something like this. So yeah, so by default, this gives your x, if I'm not wrong, I think it gives x, like P of x. Let me just write it. So this gives you P of x less than or, sorry, x is less than or equal to k. Let me just, how do I look at this? Question mark. Yeah, question mark, P binom. Yeah, so your lower tail, it basically by default, it is true. So you don't have to specify. By default, your lower tail is true. So it gives you P of x less than or equal to x. So which is this. It gives you P of x less than or equal to k. So if you specify lower tail is equal to false, it will give you 1 minus P of x less than or equal to k. So this is just not equal to P of x greater than equal to k. So it just subtracts this whole thing by 1. So you'll just get an inverse curve. So yeah, this is what you get. You see it in reverse. Like if you look at the previous plot, it looks like this. So 1 minus 0 would be 1. So which is why you see a point here at 1. And here you could see like maybe 15. Oh no, let's look at this. Yeah, maybe here 10 minus, like 1 minus this, what is it? This would be like, so 1 minus 0.6 would be 0.4. So in your next one, you can see like at 10, you see something near 0.4. Yeah, so it just like subtracts your whole distribution to 1. So that's what lower tail is. So it depends on whether you want to calculate P of x less than or equal to k or P of x greater than or equal to k. So that depends on your question in the numericals. So the next thing is the quantile. So you want to see at which value of k you get a probability of 0.6. So for n is equal to 30 and for your probability is equal to 0.3, you want to see at what k is your probability, your PMF 0.6. So here you get 10. So at k is equal to 10, you get 0.6. So that's what this function is used for. And then R binom is just to generate these random numbers in your distribution. So how many random numbers do you want to generate? So that is given by this small n here. Small n is equal to 5. So you could see that this output gives you a vector with 5 numbers. 5 numbers ranging between 1 to 30. Let's do it again. Yeah, you get some values. So all these are less than 30. And if you increase n, you'll get more. If you n is equal to 10, you get 10 random numbers. So all these numbers will follow a binomial distribution. So when you want to like look at the mean of this distribution, you could just use mean of all these random numbers, all the values of x. This will give you a mean 10.8 variance. Yeah, that's it about it. And then yeah, next we come to Poisson distribution. So here you don't have size and prob. You don't have n and p. So instead of n and p, you just have lambda, which is given by lambda. So this is your mean basically. So you have a lambda 50 and you plot a distribution. So you can see that the mean of the distribution, lambda was 50, you specified, and you can see the mean here at 50. And yeah, 1 to 300. And let's just overlay other distributions on the same plot. So if you write another plot command, it'll just give you a new plot, which means this whole outline, the x-axis, y-axis, and all this. But here you just want to add points. So you just, instead of plot, you write points and the same thing, whatever it is, you specify different color. And here we specify different lambda. And yeah, all the other things are the same. You just specify different lambda here. And you can see that your mean shifts towards the right. So lambda was 10, mean was smaller. So your curved whole distribution shifts towards the left, sorry. And your mean is somewhere around 10. It is 10. And another, you reduce your lambda even further. You make it green and you can see, yeah, your curve shifts even towards the right. Now let's just add a higher lambda. Let's say lambda is 80. And let's make it black. And you can see it shifting towards your right. Your mean is here around 8. So this is just like how a Poisson distribution looks like. And if you want to calculate the CDF of a Poisson, it's again just P poise and Q poise for calculating the quantile and R poise for random number generation. Basically the same thing like we just saw. And even for geometric distribution, it's basically the same thing. So here, like we said, we don't have n trials. You just have the probability. And this n is equal to 20 is actually your k minus 1. So that is your this. So this would mean that you got success at 21st trial. So in R, you specify n is equal to k minus 1. So this one means that you got your success at the 201st trial. So when you want to do this, you just generate random numbers. Yeah, so when if you want to plot it, you just do it like this. djom x is equal to 0 to 100. So these are all your failures. 0 to 100 failures. So because this is k minus 1, your first trial would actually be denoted by 0. So in R, it is k minus 1. It's not k. It doesn't mean k. So this is your k minus 1. So this is 1. Your first trial is 0. And your 101st trial, so this is 100. So when you plot this, you get something like this. Failure, 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 and you get success here. And anything beyond that point, yeah, you don't worry about. So it's all just 0. So yeah, this is all about how you have to do it with R. So I think now we'll look at some questions from previous year's question paper. So I'll show you how to solve them numerically, like using all the mathematical formula, and also just tell you what or which of these functions can you use with R to find the answer. So I think probably in your exams, you won't have access to R. So yeah, you might need to apply numerical formula. I'm just checking if the screen is being recorded. Yeah, okay, that's fine. Yeah, I'll share my screen on this. Okay. So yeah, the first question. In each sample of the automobile part, there's a 50% chance that any component in the part will be defective. Assume that the samples are independent and find the probability that in the next 15 samples, exactly 3 contain the defect. So this is your n 15 samples, and this is your k, 3 having the defect, and your probability is 15%, which is 0.15. So you have p is equal to 0.15, n is equal to 15, and k is equal to 3. So find the probability that exactly 3 contain the defect. So you need to calculate p of x is equal to 3. So you can use the binomial distribution here. So we know it's n choose k, p power k into 1 minus p power k minus, n minus k. So I just substitute the values here. N is 15, choose 3. 0.15 power 3. 1 minus 0.15 power 15 minus 3. So yeah, if you just solve for this, you'll get the answer. So basically, your 15 choose 3 can be given by 15 factorial divided by, like, n choose k is given by this, like, n factorial divided by k factorial into n minus k factorial. So 3 factorial into 15 minus 3 factorial into 0.15 power 3 and 0.85. So 1 minus 0.15 is 0.85. Power 15 minus 3 is 12. So yeah, you just substitute these values and you'll get some answer. So that gives you the probability of, like, probability of exactly 3 automobiles in the 15 samples being defective. So you can see how you can calculate this using binomial distribution. So with R, how do you do it now? So we have all these values, and this is just it's just the PMF. It's not the cumulative function. So you just need exactly x is equal to 3. So in this case, you calculate the PMF. Right? So if you want to calculate PMF, what do? You do D binom. D binom, and your k is just 3. K is 3. And your probability is equal to 0.15. Your size is equal to 15. So this is the command in R that you can use to solve this problem. So numerically, you use this formula, and with R you use this. What is the next question? At least 5. Exactly 3 contain the defect. Okay. So in each, so it's the same thing. Your P is 0.15. Assume that the samples are independent. Find the probability that at least 5. So you need to calculate K is greater than or equal to 5. At least, at least 5 samples out of a total of 20 samples contain the defect. So here your N is 20. Yeah, you have N is 20, P is 0.15, and K is, you need to calculate K is greater than or equal to 5. So this would basically be the summation of K starting from 5 until N is 20, until 20. And you'll have the same thing like N choose K, P of P power K into 1 minus P power N minus K. So you have summation of 5 to 20. 20 choose K, 0.15 power K, 0.85 power 20 minus K. So now in place of K, you need to substitute values 5 to 20. So it just means 5, 0.15 power 5, 0.85, 20 minus 5. Plus,
Can
now,
we use probability?
yeah, I'm sorry, somebody's saying something.
One less than probability of x less than 5. So 1 minus
You
probability
can
of
do
x,
that as well. You can also do 1 minus probability of x
x less
than 5.
than 5. Yeah.
Yeah, you can also do it that way. So that would be easier. You don't have to add all these. Like here, you have to like do a summation for 5, K is equal to 5 to 20. But here in this case, you can just do 1 minus like K 0, 1, 2, 3, and 4. So yeah, that's one way you can do it too. And with,
Madam, please share the previous year questions.
okay, yeah, these are the previous year questions.
No,
So
the document.
yeah, I'll upload this whole PPT as well with the solutions.
Okay.
Yeah, I can upload that document if you want.
Now if you have.
Yes, yeah, I can share that. So with R, now how can you do this? So you do P binom. So here it's a CDF. It's because you do a summation here, it's a CDF. So in case of a CDF, what do? You use P binom. And here your K is 4 because here 0, 1, 2, 3, 4. K is 4. So you can either do 1 minus P binom. K is 4, size is equal to 20, probability is equal to 0.15. You can either do it this way, or you can do P binom 4, size is equal to 20, probability is equal to 0.15, lower tail is equal to false, right? So we just saw that when by default lower tail is equal to true gives you less than or equal to K. So when you specify lower tail is equal to false, it gives you 1 minus P of x less than K, which is, yeah, 1 minus P of x greater than equal to K. Sorry, 1 minus P x less, sorry. So by default, you get P of x less than equal to k. So when you specify lower tail is equal to false, you get 1 minus P of x less than or equal to k. This is equal to P of x greater than equal to 5. So this is what you wanted to do in this question. So you can use either of these. Either of these methods will work. So both in case of applying the formula or solving it with R. Right? Now, let x, y, and z be three stochastically independently distributed random variables. So these are just x, y, z are random variables. They follow a binomial distribution. N is equal to 15, p is equal to 0.25. Y follows a binomial distribution where m is equal to 5, p is equal to 0.25. Z follows a binomial distribution, n is equal to 20, p is equal to
Madam,
0.25.
third and fourth question are missed.
Oh, I
Third-
think I have them later.
Okay.
Or they just follow the same exact same pattern like we just saw.
Okay.
That's why I might have skipped it.
Okay.
Yeah. I'll share the whole document with you anyway. Yeah. If you still, when you go through it, if you couldn't solve it, yeah, just write to me
Okay.
or
madam.
we could discuss it in the next class. Yeah, we were looking at this. So basically, so when you have these such independently distributed random variables and this when you have such random variables, then the sum of all these binomial random variables will also follow binomial distribution. So yeah, you will have something. So the sum of all these would be b of n plus m plus n comma p. So you don't sum up the probabilities. The probability will remain the same, but you just sum up these, the n, the number of values. So what will be the answer of this? 15 plus 5 plus 20 gives you b of 40, binomial distribution of 40, comma 0.5. So is that in the option? Yeah. This is option B. So that is your correct answer. So there was nothing to solve here. It's just like some theoretical knowledge that you need to have. Like even in Poisson distribution, you saw that they are additive. The lambda is additive. So even binomial distribution is the same case. So when you add three random variables following a binomial distribution, your new binomial your new output will also, your new random variable will also follow a binomial distribution. So now, yeah, the number of defective bytes in a hard disk has a Poisson distribution, and the average number of defects per millimeter square of a hard disk is 0.2. So whenever you see these words, average, mean, whatever, all of this, it means they have given you a lambda. Lambda is 0.2. And the surface area of the hard disk under study. So this is your sample space. The hard disk under study, okay, wait, I might be wrong. So your region under study, n is equal to 120 square millimeter. You need to find average minus 0.2, average number of defects. Okay, this is not lambda here. So that's basically your p. So to get your lambda, you have to do n into p, which is 120 into 0.2. Well, 2s are 24. Yeah, so 24. Your lambda is equal to 24 here. Surface area n is 120. Find the probability that 10 defective items. So here k is equal to 10. So I need to find. So yeah, now we have lambda and k. You need to apply this formula. P of x is equal to k. What is the formula? E power minus, no, yeah, lambda power k, e power minus lambda divided by k factorial. So when you substitute this, 24 power 10, e power minus 24 divided by 10 factorial. So yeah, you can just solve this with a calculator, you'll get some value. So how can you do this with R? So again, it's just a PMF. So when you see something k is equal, x is equal to k, you use D. Like if it's a binomial distribution, you use D binom. But here it's a Poisson distribution, so you use D Pois. And here you need to specify k. What is your k? 10, comma lambda. You write here the whole thing, lambda is equal to 24. So yeah, you just use this command, you'll get the same answer that you get when solving for this. You can try it out. Now it's basically the same thing again.
Problem, ma'am. Hello.
Yeah. Yeah.
Last problem. Can you show that?
This one.
Yeah. Ma'am, suppose 10 or fewer defective means what will be the code, ma'am?
Yes, so that's what I think we are looking here. Yeah, 10 or fewer defective bytes. So that's the
Okay.
next. Yeah, we'll
Same
just
problem.
look.
Same type or same type, ma'am? Is it same type?
Yes, it's the same thing. So it's given that it's a Poisson distribution.
Okay.
But
Okay.
here instead of P of X is equal to K, what is 10 or fewer? Oh, sorry. P of X less than or equal to K.
Okay.
This is what
Understood.
you calculate.
Okay.
So let's see what you do in this case.
Okay.
So mathematically, you just do, yeah, summation of what is x less than 10, 0 to 10. Summation of 0 to 10 e power minus lambda, lambda power k divided by k factorial. So here k is equal to 0, 1, 2 until 10. So you have to like sit and apply the summation for all of this. You'll get the answer. So with R, what you can do is, so here it's a CDF. So for CDF, you use p-poise. So if it's a PDF, like when you have x is equal to k, you use d-poise. If it's a CDF, which has something like greater than or equal to, less than equal to, you use p-poise. P-poise, so your q will be 10. Your first term will be 10 because k is 10, that's the same. And your lambda is equal to 24. It's the same thing. So fewer than, so this basically gives x less than, why am I messing up writing this? P less than equal to 10. So in the question, if they've asked greater than or equal to 10. So if the question is P greater than or equal to 10, you either have to do 1 minus P poise this thing, or you can do P poise 10 comma 24 lower limit is equal to false. So yeah, whichever makes sense to you, like whichever comes to your mind, you can use that.
24 comma lower equal to true or false. Lower.
Oh, yes, lower tail.
Lower tail. LOWER.
Yes.
Okay. Thanks.
So lower tail basically gives you a 1 minus less than equal to k. Yeah, but the answer to this question is just this. Your default, by default, lower tail is equal to true. So you don't have to specify lower tail is equal to true here. So if the question is lesser than or equal to 10, you just directly use this. If the question is greater than or equal to 10, you just use the same thing, but specify lower tail is equal to false. You just have to
Lambda
remember.
not needed, ma'am. Lambda
Lambda,
equal to
that is all the same. That always remains the same. Your k and your lambda is the same.
should we mention lambda equal to or just simply
Even if you simply write it, the commands will take it because the functions has been
Okay.
built in such a way that your first argument is k
Q.
here, which is q, and your second argument is lambda. So you can, yeah, you can practice all this. You can try it out. So yeah, when you get to explore R, you'll know. Like as and when you keep working, you'll know like where you have to specify and where you don't have to specify.
What is Q, ma'am? Q is
Q is basically your K. So it's just a
Q.
notation here. So when you use P poise, you write Q is equal to 10.
Okay.
But
Q
when
is
you
number
write,
of
but when you want to calculate Q poise, which is the quantile, there you specify P is equal to 10. It's just the way they have built the function. But generally, basically it means K. This first value would be your K.
difference between P poise and Q poise. What is the difference?
So P poise is when you want to calculate the CDF, cumulative density function. Right? Cumulative is because you have a summation here. So when you want to calculate less than or equal to 10, it has to be 0 plus 1 plus 2 plus until 10, right? So you have a cumulative probability thing. So when you want to calculate such things, you use P poise.
Okay.
And Q poise is when you want to do a quantile, which means
Exactly that
uh,
value.
yes, yeah, when this the exact value, and you want to see at what value your probability is so and so. Let me see if any of the questions. Next question. No, we don't have. I don't have any questions of that sort.
Ma'am, where can we get these commands, ma'am? This P poise or Q poise commands.
Mm, I think if you just Google like how, wait, let me try. Yeah, or maybe you can just like look for documentations to start with probability and stats with R. If you Google something like that. Or let me just Google Poisson distribution with R.
Can you give the commands in the next session, ma'am?
Oh yeah, the script will also be uploaded. And I think, yeah, even in the previous 2 live sessions, they probably used the similar scripts. I don't know if they've uploaded it, but yeah, I'll upload it by the end of today's class. Yeah, if you see here, if you just Google Poisson distribution with R, you'll find all these tutorial pages. So yeah, here you can see all these people. They've given some examples as well. So yeah, so all these are just by Googling, you can find out. But yeah, we will provide you the scripts here for
Okay.
this code.
Thank you.
Okay, coming back to this. The number of defective bytes, it's the same thing again. Your lambda is 24, which is 120 into 0.2, and your and your k is 15. So you need to determine the probability that 15 x is greater than or equal to 15 defective bytes. So we just saw in the previous question. So what is this? X greater than or equal to 15 is equal to 1 minus p of x less than 14. So either with R, you can do 1 minus p poise 14, comma, lambda is equal to 24. You can do this. Or p poise 14, comma, lambda, comma, lower dot tail is equal to false. So this will give you your answer. And mathematically, it's just 1 minus p of x less than or equal to 14. So 1 minus summation of 0 to 14 e power, no, lambda power k e power minus lambda by k factorial. So yeah, mathematically and with R. So if you look at all these 3 questions, they basically apply this, it's the same distribution, but you just have different things that you have to find, like x is equal to k, x less than k, x greater than k. So you just have to be careful about the question. What is this? So the number of LED lights produced daily at a certain factory is Poisson distribution with mean is equal to 5. So here K is equal to 6 basically. So what is the probability that the number of defective LED lights does not exceed 6, right? So K is equal to 6. And here it's given over a 3-day span. 5 LED lights. What is the question? 5 defective lights are produced in 3 days. So your lambda is 15 here. What should you calculate? Probability that number of defective lights does not exceed 6. So it's basically less than equal to 6 you need to calculate. It does not exceed 6, which means the maximum has to be 6. It should not exceed 6. So P of x less than or equal to 6. So 0 to 6, e power minus lambda, lambda power k by k factorial. So with R again, it's just P poise, Q is equal to 6, lambda is equal to 15. Yeah, this should give you the answer. So the next question, if the probability is 0.7 that a candidate will pass an exam on any attempt,
Madam, request you to solve even 10th and 11th problem.
repeat it. Oh, sorry.
10th and 11th. So skip 10th and 11th. 10th one and 11th one.
I'm pretty sure I skipped it because it's the exact same pattern. I'll share the questions with you anyway.
Okay,
Yeah, you
okay.
can. What is this? So the probability is 0.7 that a candidate will pass an exam on any attempt. So the kth attempt, the candidate will pass. So this is like a geometric distribution. So what is the probability that the candidate will finally pass the examination on 5th attempt? So here k is 5. You need to find the probability of x is equal to 5 that he passes on the 5th attempt. So we saw that the geometric distribution is p into 1 minus p power k minus 1, right? So you just substitute the values here. P is 0.7, 1 minus 0.7, k is 5, 5 minus 1. So 5 minus 1, so 4. So basically, yeah, probability of success into probability of failure divided to the power of number of failures. So this will give you the answer. So you can just directly solve this as well with R. So you can just do 0.7 into 1 minus 0.7 to the power 4. You can write something like this. Or you could also write, what is that? D-jump. You write k minus 1. Wait, let me just have a quick check. D-jump. Yeah, so here you write k minus 1. So you write in R, you write D-jump, k minus 1, comma, probability. P is equal to, sorry, not P is equal to, it should be prob is equal to 0.7. So yeah, this is how you do it with R. You can do it either directly by just substituting the formula or by using this function here. So yeah, the next question is, we saw the theory of this. So this is just directly like remembering these formulas and just choosing the answer. So, or yeah, urn contains N blue and M red balls. Balls are selected at random one at a time until a red ball is selected. So M means success. So if we assume each selected ball is replaced before the next ball, Probability that exactly n rows are needed until red ball is selected. Exactly n rows. So you just remember this formula here. Oops. Okay. Let me go back. Exactly n rows. Yeah, so this is the formula. You can see here. So that, yeah, just. And here the other question is they've asked what's the probability that at least k draws are needed until red ball is selected. So for that you have to remember the other formula. So this is one formula and the other formula was this. At least k draws are needed. So this one. Right? So these are just something you remember. And the next question, which one of the following command in R software will compute P of x less than 8, P of x less than 8, where x follows a geometric distribution with the parameter 0.7. So if you want to compute less than 8, you have to compute a CDF. So when you want to do a CDF, what should you do? You have to use P geom. Because the question they've asked geom. So P geom less than 8, right? So in R, what should you specify? You have to specify k minus 1. Here k is equal to 8. So k minus 1 is 7. And prob is equal to 0.7. So that is, so this is your answer. Option B is your answer.
One more D is there, ma'am. What is that?
Option D is dgeom. So dgeom, you use dgeom when you want to calculate P of x is equal to 8.
Equal to
Exactly equal to 8. So this is for a PDF.
D,
Right?
PDF.
Yeah.
For D
So
only, P is equal to D8.
yes. So PDF, when you want to do some PDF, you do dgeom. When you want to calculate CDF, which is pgeom. So basically, like how you can remember this is by, how do I insert a new slide? Okay. Sorry, it's not a PDF, it's PMF, probability mass function. So so you have probability mass function, you have CDF, you have quantile, you have random number generation, right? So PMF is basically P of x is equal to k. CDF is P of x greater than equal to k or P of x less than equal to k. And quantile is which k value you find a probability, something like that. And here you have to generate random numbers. So this is how you can identify from the problem statement of which one you have to use. So for binomial distribution, so we saw binomial, Poisson, geometric. So basically for these, so for binomial distribution, if you want to calculate P of x is equal to k, which is a PMF, you use D binom. And similar Poisson, it's D Pois and D geom. And if you want to calculate something like x is greater at least 10 books, at least 10 defective parts, or greater than at most 6 tosses. Some question, if the question is like that, you need to find these values.
Madam, here in the question it is probability of x is less than something like 9. It is not less than or equal to. Then in that case we have to use p poise. It is a CDF, no?
Yes. Yeah, that's what you've used here. We used pgeom.
P
Like
geom.
here, I'm using a pgeom.
Okay.
So here you use, sorry, this was wrong. What is this? How do I erase it? Okay, never mind. Ah. Okay. So yeah, if you want to calculate CDF, it's P binom for a binomial distribution, P poise for Poisson, and P geom for geometric distribution. And if you want to calculate quantile, it's Q binom, Q poise, Q geom. And random, if you want to generate random numbers, R binom, R poise, and R geom. Yep. So for these, you in the bracket you will specify K comma size is equal to N, probability is equal to P, right? So this would be the same for binomial, it would be this. For Poisson, you just have to specify your K comma lambda. For geometric, again you have to specify K minus 1 comma prob. Right, so these are just some things you have to remember with R when you solve it with R, right? Yeah. So this week's assignment will also be follow exactly like similar patterns. And you should
Ma'am,
be
you quantel, give one example, madam. Any one example under binomial Poisson or
yeah. Q binomial. Or okay, let me share my screen. Stop. So here, let's say, P is a quantile. So in a population, in a like, if the total number of trials is 30, you want to find the 60th quantile, right? So after which value will you get the like 60th quantile, like at which value? So that is what you need to calculate, and the given probability is 0.3. So yeah, if you just run this, you'll get something. Sorry, what did I do? If you run this, you get a value of 10. So this means that K is equal to 10, you get your 60th quantile.
Ma'am, could you please explain the argument of lower dot?
So let's consider a binomial distribution. Let's consider a CDF. So let's say you just plot this thing. So by default, when I say by default means you don't have to write it there, but it's already inbuilt in the function. So when you don't specify an argument, the function takes in the default value. So the default is true here. So what does that mean? So when default is true, what does this thing calculate? So when lower tail is equal to true, P binom calculates the probability for x is lesser than or equal to k, right? But in some instances, like we saw some examples, we need the probability greater than equal to k sometimes. So when you need greater than or equal to k, you specify lower limit is equal to false. So basically what it does is, it does 1 minus p of x less than k. Yeah, so it basically does this. So when you need p of x greater than or equal to k, so mathematically we write that as 1 minus p of x less than or equal to k, right? So instead of that, you just specify lower tail is equal to false. And it just reverses this whole curve, like you can see here. So that is the basic idea of this argument.
So, ma'am, we don't need to put the actual value, but we can give the argument lower dot tail equals to false in
Yes,
case we want to find out the value x greater than k.
yes, exactly.
Greater than k. Okay, greater than
Yes,
or equals to k, no?
greater than equal to. Yes, yes. Here
Okay.
I can't type that here. So yeah, greater than equal to.
Okay, thank you.
Ma'am, what is the use of that getting that plotting the um, plotting the diagram? What are the applications of the diagram?
There, there's no application of the diagram. It's just for you to visualize, to see the distribution. Like sometimes you just can't be looking at the numbers. But if you look at these values, it'll be much simpler. You can easily interpret from this key, like for so let's say there are three distributions, like you're modeling something, you're doing some machine learning model or whatever. So you have, let's say you have three models and they all follow the same Poisson distribution, but you just specify different parameters. Like sometimes you'll have to tune parameters, like which mean gives you the best outcome, something like that. So when you do that, when you want to evaluate performances, when you look at the curve, yeah, you'll kind of know. So like from this curve, you'll see the black curve, it has the highest mean, and green has the lowest mean. So yeah, it's just to get an idea of the whole distribution. So yeah, when you look at the numbers like this, when you look at these
Very
numbers,
difficult.
yeah, you can't make any sense out of it. Like even if you try to remember the pattern, you cannot make much sense. But when you
Uh,
plot it, you can exactly looking at that, you can know where the mean lies, and
where it,
what the
where it
whole.
increases, where it decreases, we can identify easily.
Yeah. So even here in the CDF, you can see where it increases and where it flattens. So it's probably the failure is here and the success is somewhere here. This is what it means. And all
Oh,
of these are nothing. It's like greater than the success. So x is
oh,
greater than 1. This is x is equal to 0. So this is x is between 0 to 1. And this is x is equal to 1. So yeah,
thank
looking at this curve, you can find it.
you. Ma'am, one more doubt. Which of the following alternatives to the some command? What is the that meaning of that? Alternative can be the outcome of the command, or
What
is
that
alternatives can be the outcome of the command.
is that
Some
written somewhere? Or
some or voice n equal to 10, lambda equal to 6.
I don't remember.
Alternatives can be an outcome of the command.
I have not written that anywhere because alternatives, outcome, possible outcomes, number of. I'm not sure what
I
you're
tell
at.
you one command r qois
Are poise?
r poise n equal to 10,
Okay.
lambda equal to 6,
I don't
or
think any lambda is equal to 6
no,
here.
I am asking separately the question.
Oh, you are just asking me a question.
Yeah.
Okay. Oh, you want me to plot that?
Yeah. R
But
square
poise will just give you a random number. It generates a random number.
10, comma 6.
Is this right?
Okay.
Yeah, so this basically gives you 10 random numbers that lie between 0 to 6.
Oh, 10 random number.
Yeah. Random. So
Alternative,
this whole,
alternatives.
I don't understand what that alternative means.
Alternative can be the outcome of the command. So one of the problems.
So yeah, when you generate random numbers, like I can run this command, I'll get some answer. You run this command, you'll get some answer. So we all won't get the same answer. But you need to understand that this command will give you 10 digits within
Oh,
So yeah, so you can choose like any of the options. So like probably like you have in the question paper, you have been given some options, but when you run that in R, you won't get the exact option. So you don't rely on R in this type of questions here.
Possible to get
This,
a float number, that means point something for this command. Is it possible?
yeah, it is possible. Yeah, you can get floats.
It is coming as
So
for
when a
10.
random number, so it depends on what your experiment is. Like if your random number is a toss of a coin, it cannot be a float. But if your random number is the mark scored in an exam, that can be float.
Okay, for this command, only 10 numbers, 10 random numbers only coming. That is,
Okay, yeah, that doesn't.
but the 10 numbers, two options are there. One is integer, one is that float.
Yeah,
All are 10, which to be selected?
so yeah, if you don't know what a specific function does, you can write question mark followed by the function. So question mark rpoise, it'll give you the whole documentation. Like you can see in this help window, you can see the
Okay.
whole documentation of this. So it will tell you what all parameters. So rpoise just n comma lambda. I don't see any float here.
Only
Yeah, I'm not.
integer value only or float value is there?
Yeah, I think it gives you only integers. Yeah, because they've not specified anything else here.
Both options are there. Float value as well as integer value. That two options only 10 values. Other options are less than 10.
I
So
think it
that
just gives integers. So when you look at this, so
yeah.
in case if this command can give you float, there should have been another argument like float is equal to true something, but you don't see anything. It just says vector of non-negative means.
Okay. So here coming that only integer only, so that we can decide float will
Yeah.
not come.
Yes.
And ma'am, the values of the 10 outcome will lie between.
Yeah. Until 6.
But the
Like 0 to
values
6.
But values greater than 6 are
grade.
coming.
Yes.
So rpoise is just to generate random numbers. Here you don't need like greater than 10, like greater than k, less than k. You're not finding the probability of an event, like probability of your outcome being less than 10. You're
But
just
numbers,
generating,
numbers.
yeah, you're just generating 10 random numbers.
Again, if you type, will it come? Will it give the same command? Will it
No,
give?
that's
Will
what
it
I'm saying. It will not give you the same command.
same
It
number
will
will not come?
you see,
Oh yeah,
so yeah, it will be different. But if
different.
you want a same command, I don't know if this could be true, but in R, there's something called set seed. So you can write any number here. So if you set 1, 2, 3, then now you generate rpoise lambda is equal to 6, you get this. Now again, I do oh, it doesn't work. Never mind. Yeah. I thought I was just trying something, but no. So yeah, every time you repeat this command, you won't get the exact same numbers.
Okay.
Yeah, that's the thing.
Okay. Thank you.
Yep, that's it. Load. Okay. If no more questions, yeah, we can end the session. Upload. Do you all have the link to the drive? Copy. Yeah, I'm just. So this is.
Madam, share that link, madam. Okay.
Yeah, I've shared it in the chat box. So this is the link to your drive. And all the recordings can be found in the YouTube channel. I'm just copying the link to last week's live lecture. But yeah, you can find all the lectures in the playlist NPTEL. So there's a playlist called NPTEL data science with R something. So yeah, you'll find all the lectures in that channel. Yeah, these are the important links. I'll upload. Yeah, downloads. I am yeah, I'll upload. Yeah, I've uploaded this PDF now. Let me look for the last year's questions. So I've uploaded the R script as well. Assignment. Yeah, I'm just looking for the assignment document. I'm not able to log into the portal right now. Oh, wait. Week 6. Solution. Okay. PDF. Yeah, I've uploaded the assignment, last year's assignment as well. Let me just rename all these. 37. Right, yeah, I've uploaded all the documents on the drive. The YouTube video should be uploaded tomorrow morning when you wake up.
Madam, at morning at what time it will be available, madam?
Also, yeah, like it should be available like 8 o'clock.
Morning 8 o'clock.
Yeah.
Okay, madam.
Yeah. All right. If there's nothing else, we can end the the class today. And yeah, the next lecture will be on next Tuesday,
Okay, madam.
6 to 8.
Thank you so much.
Yep.
Thank you, ma'am.
Thank you. Thanks
you.
for joining. Bye.
Bye.